All right, good afternoon everyone and welcome back to our stream. So today we have quite a few things that we would like to discuss today. So again, just as usual, I shall be waiting here for a few more minutes before starting actually. And again, if you have any query during the class, feel free to post them on the live chat. I shall be definitely answering your questions there. So today we shall be talking a few of the most important concepts in any microprocessor technology. In fact, this is associated quite heavily with any modern programming language as well. Okay, and we shall see how that's the thing. Okay, so we shall talk about something called the stack, and in association with stacks, we shall discuss subroutines. So we shall basically discuss stacks and subroutines, and then with respect to the Intel 8085 microprocessor, we shall be discussing the call return statement. Okay, so we shall discuss these things today. All right, so again, if you have any query, feel free to ask them on the live chat. I shall be answering your question here, and feel free to ask any question if you think the question might be stupid. Okay, of course, and no question is stupid, right? So even if you think you have a silly question, feel free to ask. Okay, all right, so with that said, so I shall continue the class in a bit. All right. All right. So in today's discussion, let's recall a few things. Let's try to recall a few things that we actually did earlier, right? And again, this is going to be a two-part discussion. Today we shall discuss some of the things, and on the next class we shall discuss a few more things regarding the stack and call instructions, right? Stack and subroutines. All right. So let's recall a few things that we have studied earlier, right? So while executing a program in the 8085 microprocessor, what happens? The microprocessor keeps track of the instructions by setting the value of the memory address of those particular instructions in the program counter, right? So in a sense, the program counter is a 16-bit register which is responsible for counting the programs, or rather counting the instructions. So what it does, it keeps a track of the memory addresses of all the instructions, right? For example, if I have a very simple program that starts at memory location, say for example 8050, so at 8050 memory location, maybe I'm doing something like maybe let's write down a simple program, right? MVI A, 25. So I'm copying this 25 hexadecimal value to the register A, and I'm writing this in memory location 8050 and 8051, right? That's understandable, right? Because it's a 2-byte instruction. Of course, subsequently, the next instruction would appear at memory location 8052, because this was a 2-byte instruction. So 2 bytes of memory would be taken up by this particular instruction. So let's write down MVI B, 35. Right? So now my register B has this this value 35, and then again this is a 2-byte instruction. So that way, the next memory location in which we can write something is memory location 8054, because memory locations 8052 and 53 has been taken up by MVI B, the opcode for MVI B, and 35 respectively. And here, so let's do add B. So what am I doing? I'm adding the content of register B with that of the register A and storing the result in register A. it's a single byte instruction, so yes, we can do that very easily. And say in the next memory location, I'm just halting my program, right, with a halt instruction. So it's a very simple program to add two numbers, right, in the microprocessor itself. So now let's recall, when we started the program, we had to put some assembler directives, right? And if you're doing it in a proper microprocessor kit, right, if you're doing in a physical microprocessor kit, what you will do, you will set the value of the program counter by setting reset and the memory address and then hitting execute or go, something like that. So that actually sets the initial value of the program counter itself, right? So what we did earlier, we actually put a assembler directive, and in that assembler directive we wrote that we asked the assembler to make sure to set the program counter initially to the memory address where the program actually begins. Alright, so this is what happens. While starting the program counter gets an address of 8050, right? So the program counter, while starting the microprocessor or while starting the execution, the program counter gets a value of 8050, right? So it starts looking at this and executes this program, this instruction. And after executing this instruction, the microprocessor of course increments the program counter by a value of 2, because the microprocessor itself knows that it just executed a 2-byte instruction. So the program counter now expects the next memory address where the next instruction should reside is this. So after execution of this particular block, or rather this particular instruction, the program counter is set to this value, so that the next instruction that is executed is this one. And after execution of this instruction, the microprocessor once again knows that the program it executed, or rather the instruction it executed, it was a 2-byte instruction, right? So what it does, it increments the program counter once again by a value of 2. So it becomes 8054, right? So after execution of this instruction, okay, so what happens? It gets a value of 8054. And once it executes this instruction, this again once again knows. Now, so now after execution of this instruction, the program counter becomes 8054, and then it of course looks for the next instruction at memory location 8054, right? So of course now this executes this instruction, and after executing this instruction, the microprocessor understands that it executed a single byte instruction, right? So it would increment the program counter by a value of 1. So it would become 8055. All right. So it goes to the next instruction basically, okay, and which is residing at memory location 8055. And subsequently, what happens? The program counter, and of course, after executing the halt instruction, the program counter is not incremented at all. So the microprocessor goes into a bus idle state. So that's the end of the program. So I just said this as a so that you can recollect how. So that you can recall how a microprocessor actually executes a certain program, right? So by means of keeping track of the instructions through the program counter itself. So program counter is pretty much responsible for keeping track of what to execute, right? It keeps track of what to execute. If somehow, due to our mistake, not due to the microprocessor's mistake, due to our mistake, if somehow the program counter loses track of what to execute, the microprocessor will basically hang, or something wrong will happen. Something terrible might happen. Okay. So it is always our duty to ensure that the program counter actually kind of knows where to look for the next instruction, right? It does it automatically, but if we do some shenanigans here, which we are going to do today, okay, we have to make sure that the program counter is capable of keeping track of the next valid instruction that we want to execute, right? So with that preamble aside, let's discuss our particular topic today, right? So we are going to discuss something called stacks. Now, by means of studying, so you previously have studied computer architecture, right? I think some part of data structure and things like that. So there you probably have studied in greater details probably about stacks, right? So stack is particularly a data structure. Now, of course, when this microprocessor was actually being used by people, and we're talking about 1970s, right? Then you didn't have generic programming languages, and the concept of data structures wasn't that much relevant for anybody, right? So people invented their own data structures for doing their own tasks. Okay, things were not streamlined that much, right? But the concept of stack was there. So what is a stack? Okay, let's discuss that. So we are now talking about stacks. Oh, what did I write? All right. So again, anytime if you feel that you don't understand something I just said, feel free to ask me in the live chat. I shall definitely be answering your question. All right. So stack, as engineer, you can just think about it as a bucket of memory. Okay, a bucket of memory. So what happens? Consider a simple bucket, right? And I believe all of you have seen a bucket, right? So it's a bucket, right? And in a bucket, say for example, you have put something here. And if you have an empty bucket, if you put something in the empty bucket, what happens? It goes to the bottom of the bucket, right? Right. Then if you put something else, then that goes on top of what was there in the bottom of the bucket, right? Understandable, right? That's quite understandable. Then you put something else, so that goes on top of that. So if you put something else, that again goes on top of that. Okay, so whatever you keep on putting goes on top of the last thing that you actually had put inside the bucket, right? So a stack is essentially like a bucket. Okay, whatever thing you put, now you try to understand this thing, right? So this was the first thing that you had actually inserted into the bucket, right? So that went to the bottom of the bucket. So this was the second thing that you inserted into the bucket, and this was the third one, this was the fourth one, the fifth, and the sixth. So imagine these are the things that we have in the bucket, right? All right, that's quite easily understandable, I believe. All right, now you want to pull things out from the bucket, right? Right? This mechanism by which you put things inside a bucket in microprocessors terminology is called a push. You pushed something inside the bucket, right? So this is the order in which you push the different things inside the bucket. So this was the number one thing that you pushed inside the bucket when the bucket was empty. So it went to the bottom of the bucket, and as you pushed newer things, those went on top of the last thing that you had pushed, right, inside the bucket. Now imagine you want to pull things out of the bucket. Now if you want to pull things out of the bucket, it's called a pop instruction. Okay, so this terminology is there. I mean, this terminology is quite universal, right? Push and pop, right? Now if you want to pop things from the bucket, so for example, in a bucket you have put many things, right? But if you want to pull out things, of course, what will happen? The thing that went last into the bucket will come out first. Okay, and the thing that went first into the bucket will come out last. Is that understood? So this thing that I'm designating with number one, that went inside the bucket first, right? That was the first thing to go into the bucket. And if I now pull things out of the bucket, what happens? This thing that went first into the bucket will come out last, right? That's understandable, right? So the thing that went last will come out first. So the order in which I shall be able to fetch, or rather pop things out of these, would be 6 first. This item will be pulled out first. Then after pulling that out, I shall be able to pull out this item first, next, then this item, then this, and at last the one that went into the bucket first, right? So that's understandable. And this kind of terminology, where we have this kind of mechanism where I have a memory, so this is actually a memory block we shall discuss. So I have something, a data structure or something like that, where I put things, okay, and then pull up things, but the order actually automatically switches back. So in this particular mechanism, the thing that went into the basket last, okay, rather the thing that went into the stack last came out first, right? So this is called a last in, first out architecture. It's a LIFO architecture, for example. Okay, last in, first out. The thing that went in last will come out first, then the next one, then the next one, then the next one, right? So that way. So if you have any query, feel free to ask at this point, because this is kind of inherent into any microprocessor technology. In fact, any programming language actually supports this stack, right? So anytime, for example, you are writing a C program or Python program or something like that, things are actually stored into the stack. You also have something called a heap, but we are not going to discuss that. But essentially, when you declare a variable in C, that actually goes to the stack. When you declare an array, something like any variable in C, for example, that by default goes to the stack. It's saved into the stack. Any operation actually saved into the stack, and so on and so forth. Anyway, those things happen inherently, automatically. So of course, for us, we have to do it manually here, because we are dealing with the computer itself, okay, without any higher level programming language. But again, feel free to ask any question that you might have. And also, if you understood everything, feel free to let me know. Otherwise, it becomes difficult, or slightly more difficult for me to understand what is happening with you people, right? Because this is not going to be this is not being a face-to-face interaction, right? All right. So if you have understood everything, feel free to ask. Feel free to let me know. And if you have missed something out, or if there is anything here that is not understandable, feel free to ask. All right. So it seems like no one is writing anything on the live chat other than good morning, good afternoon, right? Please, someone write something so that I get a feedback, right? You studied control system and you know feedback is very important in life, right? Other than having a feedback, I won't actually really know what is happening with you people, right? All right. So similarly, for the microprocessor, particularly, all right. So particularly in this microprocessor, 8085 microprocessor, okay. So what you also have a stack, right? So now here comes the usefulness of the stack pointer. So recall the stack pointer. We designated that with SP. It's called the stack pointer, right? So it's the stack pointer. What it points to is called the top of the stack. Right now, just say I initialize the stack pointer to a particular value. Say with this instruction. Of course, it's a 2-byte register. Okay, right? It's a 16-bit register. So I can initialize this with a particular value, right? Say let's say I initialize this with, say, what should I say 5555. Who knows? All right. So I initialize the stack pointer with this particular value, say 5555, right? Something like that. So what happens is, now look at the memory block of the microprocessor, right? Let's look at the memory block. Right? So again, you understand that the memory is basically a continuous block, right? A contiguous block, for example, here, right? So let me write down the memory location. So for example, say this is memory location 5555. All right. Say this is memory location 5556. This is 5554. So I'm just looking at a particular section of the memory. Okay, I'm telling you what is happening here. All right. All right. So this is the particular memory block I'm interested at. Okay. Particular memory block I'm interested at. Right. So right now what I have done, I have set the value of the stack pointer. Okay. So what is happening is the stack pointer is pointing at memory location 5555. Okay. So essentially what is happening, the stack pointer is pointing at this particular memory location. Okay. All right. Just keep that in mind at this particular point. Keep that in mind. Okay. Now at this very moment where the stack pointer is pointing at a particular memory location, okay, you can imagine this memory set has become something like a bucket. You can imagine this memory set has become something like a bucket. Okay. This entire stack of memory has become something like a bucket, and this is quite literally the bottom of the bucket. Okay. This is quite literally the bottom of the bucket right now. All right. This is quite literally the bottom of the bucket. Try to understand what is happening. Okay. All right. Good. Again, if you don't understand something, feel free to know. Feel free to let me know. So again, try to understand that this is the bottom here of the bucket, right? Right. So if I now put something into the bucket, where does it go? It goes into this place, right? Because this is quite kind of the bottom of the bucket that is designated by the stack pointer, right? So let's now write a bit of program that actually does something with this. Say after this instruction, let's say I'm setting the value of some. Let's say I'm setting the value of the BC register pair, okay, with certain value, say 1, 2, 3, 4, I don't know. All right. So if I do that, what happens is after executing the instruction, what happens? After doing that, what happens? B register gets the value of 1, 2, and C register gets the value of 3, 4, right? So after doing this is what happens with register B and C. Okay. Now I'm showing you how the stack actually works, and soon you shall see how it actually is used in practical applications, right? All right. So now let's look at this. Let's look at the next instruction. So if I say something like this, push and say B. Now in the 8085 microprocessor, push, okay, can be used only with push and pop. These instructions, I'm going to discuss all these things. Push and pop. These instructions can be used with register pairs only. Okay, push and pop instructions can be used with register pairs only. For example, if I say push B, what happens is that it pushes register pair B and C. Okay, it pushes BC register pair into the stack. All right. So it pushes the BC register pair into the stack. So after that, if I do push B, what happens? The value of BC register pair actually gets pushed onto the stack. Okay, let's see what happens. So if I do that, what happens? B had a value of 12, so it will go to this place, and C had a value of 3, 4. It goes to this place. All right. it goes to this place. All right, let me know if you understand this. All right, and then what happens is, or rather, let me just so this is the bottom of the stack, right? Bottom of the stack. All right, so what happens is, I mean, this is the threshold point, something like that. Nothing can be stored beyond this point. So if I do this push instruction here, what happens? 12 is stored here and 34 is stored here, and the value of the stack pointer gets incremented to now, so that it now points to this particular memory location. So you understand what is happening here. Okay, so when I push something into the stack, what happens? The stack pointer's value get incremented by a value of 2. So the stack pointer got decremented by a value of 2. Okay, so the stack pointer's value got decremented by a value of 2. So it was originally pointing at memory location 5555. So it meant that memory location 5554, 5553 were ready to be occupied. So now this is the bottom of the bucket, right? This is the bottom of the bucket. Okay, and this has been now occupied here, right? Understandable? So this is now, this place is now denoting the bottom of the bucket. All right, try to get the point. All right, so now with that said, let's set some other registers. Let's say LXI D, 78AB. All right, and if I now do something like this, so DE register pair has got a value of 78AB. If I now do push D, so what happens is that the value from the DE register pair gets pushed into the stack. So again, this is now the bottom of the stack, right? Rather also sometimes called the head of the stack. This is pointing to the head of the stack, but currently this is the bottom of the bucket, right? So what happens is that this value actually gets pushed into the stack. So this is going to get 78 and this is going to get A, B. Okay, all right, and subsequently what would happen is that the stack pointer would once again get decremented by a value of 2, so that it can actually now point at memory location 5551. So this is now denoting the bottom of the bucket. All right, so the stack pointer always points to the head of the stack. We call it the head of the stack or top of the stack. Stack pointer always points to the top of the stack. Okay, stack pointer always points to the top of the stack. All right, so I think that's understandable. All right, so stack pointer would be actually now pointing to this memory location. So if there is any confusion regarding anything, feel free to ask at this point. Feel free to ask at this point. All right. All right. So complementary to this stack, to this push instruction is the pop instruction. For example, now if I say something like this. So currently, what do I have at the top of the stack? I have these values at the top of the stack, right? I have these values at the top of the stack. Now, if I say something like this, if I say pop H, what happens? If I say pop H, what happens? What happens is that, let me just copy paste it first so that actually you get the idea. Let's look at this very carefully. So on the top of the stack, what do I have? So this was a result of a push instruction. This was a push instruction, and this was also a result of a push instruction. Now on the top of the stack, what do I have? I have AB and 78. I have these two values, right? AB and 78, rather 78 AB. I have these two values, right? So now if I do a pop instruction, what happens? These two values are popped from the top of the stack. It's like, so the push instruction is like pushing something inside a bucket, and pop instruction is like pulling things out of the bucket, right? So when you do pop, what happens? The thing that went into the bucket last will come out first, right? So if I do pop, what happens? These two values are popped out of the stack. Okay, so these two values are popped out of the stack, and by just popping them out of a stack wouldn't do anything unless I copy it somewhere, right? So I did this instruction pop H. So what happened? So if I do pop H, what happens? What happens is that the top of the, again in 8085 stacks, the stack works in 2 bytes, right? So every time you push something, you have to push 2 bytes of memory. Okay, and whenever you pop something, you also have to pop 2 bytes of information, right? So the top of the stack is popped into register pair HL. So try to understand what is happening here. So the top of the stack is actually popped into the register pair HL. So if I do pop H, then what happens after this? What happens is the stack pointer is incremented. So the stack pointer gets incremented. So the stack pointer, instead of pointing at this memory location, now actually points to this memory location. So the stack pointer is actually points to this memory location. So this is now the head of the stack. So this indicates that this has been taken up, right? This has been popped up, for example, and so the stack pointer gets a value of +2, for example. So this is pointing to what was below the previous thing, and the value that was popped up, which was like AB 78 AB, will now be stored in register pair HL. So now after doing this, the H register will get 78 and L register will get AB. You got this, right? You got that, right? Alright. So with that said, let me ask you a very simple question. For example, say I have done something like this. I have done LXI H comma 1 2 3 4. So HL register pair has a value of 1 2 3 4, and I have done LXI D comma 5 6 7 8. So DE register pair has a value of 5 6 7 8. Now my question is, I want to exchange the values of DE pair with those of the HL pair. What would I do? So this is my question right now. So I want to exchange the values stored in HL register pair. So for example, now HL register pair is containing 1 2 3 4, and DE register pair is containing 5 6 7 8. I want to exchange these two, so that I need to write a program that executes an exchange operation. That what it does, it actually copies 1 2 3 4 into DE register pair and 5 6 7 8 into HL register pair. It does something like that. It exchanges the values. What am I going to do? and again without using a third variable, something like that. So you did things like that in your C programming classes, right? Something like that. Okay, I give you two values, for example, in two variables, and you have to exchange those values, for example, here. Okay, and without using any third variable, for example. So you did some weird addition and things like that. We are not going to do that here. So we are going to employ the stack here, for example. Okay, so I have these values, for example. Now yeah, we had a network issue, and I think it's resolved now. So please join back. All right. All right. Alright, so as we have been talking, for example, say my register pair HL has a value of 1, 2, 3, 4, and register pair DE has a value of 5, 6, 7, 8, right? So let's say we have to initialize the stack pointer, for example. Okay, so let's initialize the stack pointer with any suitable value. Just as before, let's initialize this with 5, 5, 5, 5, for example. All right, so my stack pointer is now pointing at this memory location, right? So this is 5, 5, 5, 5. This is 5, 5, 5, 4. This is 5, 5, 5, 3. All right, so this is representative of the bottom of the stack, right? This is representative of the bottom of the bucket, for example, in this regard, right? So now after doing this, I have these values in HL register pair and DE register pair. If I do things like this, try to understand what is happening. So if I do push D and push H, what happens after doing these two? If I do push D, what happens? The value from the DE register pair goes into the stack, right? Now in the DE register pair, I have 5, 6, 7, 8, right? So 5, 6 goes here, 7, 8 goes here. Now my stack pointer will be pointing at this memory location, right? So now stack pointer is now pointing at this memory location. Then I do push H, for example, right? So then I do push H, for example. So if I do push H, what happens? The value from the HL register pair goes into the stack. Now what is the bottom of the stack? Of course, so rather what is the bottom of the bucket here, for example, here, this one, right? So what is the value in the HL register pair? That's 1, 2, 3, 4. That goes into this one. That goes into this one. And the stack pointer automatically gets decremented by a value of 2. So the stack pointer actually points here. Alright. Now after doing that, now these values actually have been stored in the stack, for example, right? So now if I do something like this, pop D and pop H, what happens? What happens? So now previously D had a value of what was the value stored in D? D had a value of 5, 6, 7, 8, right? Previously. Now I am doing pop D. What does pop D do? Pop D would basically take the value from the top of the stack. Again, any pop instruction would take the values from the top of the stack and pop it into the register pair. So these values will now be popped into the register pair DE, right? So these values will now be popped into the register pair DE. So the register pair DE would now get a value of 1, 2, 3, 4, which was originally the value of the register pair HL, right? So these two values will be now popped into, so if I do the pop D instruction, what happens? The DE register pair will now get the value of 1, 2, 3, 4. And after, of course, doing a pop instruction, the program counter is incremented by a value of 2. So here the program counter points to this one. Now after that, if I do pop H, what happens? This value, whatever was stored in the top of the stack, for example here, this was stored in the top of the stack because this is the memory location 5553, which is being pointed by the program counter. So this particular stack, this particular set of memory will be now popped into HL register pair. So after that, if I do pop H, what happens? The HL register pair gets a value of 5, 6, 7, 8. So originally HL register pair had a value of 1, 2, 3, 4. Now DE register pair has got that value of 1, 2, 3, 4. And similarly, originally HL register pair had a value of 5, 6, 7, 8. Now HL register pair has got a value of HL register pair has got a initially HL register pair had a value of 1, 2, 3, 4. Now, so this was 1, 2, 3, 4, and this was 5, 6, 7, 8. Now after doing this push and pop, what happens? The pop register, the D register pair has now a value of DE register pair now has a value of 1, 2, 3, 4, and the HL register pair has a value of 5, 6, 7, 8. That is how we have now exchanged the values of two register pairs. That's one of the important things that you can actually do. For example, in this, right? Okay. All right. So no confusion up to this point, right? So this is a way in which you can actually copy paste values of register pairs as well. Okay. All right. So you can put things in the stack, and you can consider the stack to be a temporary placeholder for different memories, different register values. Okay. You can consider the stack to be that. All right. All right. All right. So let's discuss one of the most important things here. Okay, one of the most important things here. For example, so in C programming, for example, you have probably studied something like this, right? So you have a main function, for example, you always have a main function. For example, in a C program, you always have a main program. For example, say int main something. Okay, and there, for example, say I'm adding two numbers. For example, let me just write down a very simple program. Say int x equal to, so for example, 5, int y equal to 6, and I want to add these two numbers, right? So now instead what I'm going to do, I'm going to rather call a function. For example, so I'm saying int sum. I'm going to call a function. The name of the function is addition, and I shall pass up these two variables x comma y. Okay, and that would actually sum up, right? Sum these two numbers. Now of course what I'm doing here is that I'm calling a function, okay, that resides outside the main function. Okay, so for example, in this particular case, I shall have a function that looks like this: int addition. For example, in C, of course, int addition, int x, int y, and then I shall have something like return x plus y. Yeah, something like that. So try to understand. This is called program control here, for example, right? So the program control was actually, again, similar to a program counter. The program counter was executing the program that was in a very sequential order, right? This was already all inside the main function, right? Now there, at some point, it encountered a program or encountered something for which it will have to go outside the main function, right? So this is the main program, right? This is the main program, and now the program counter will have to now move outside the main program, right? So it moves. So when I call this addition function, what happens? This function is called, I say this function is called, right? Try to understand. This function is called. So what does it mean? It means that this function was outside the main function, and now somehow the program control has moved to that particular function. Okay. Now with these values of x and y, I am calling this function, and this function is giving me some result. And with that result, I shall come back to the main program. So that is the whole point of calling a function. Okay. So if I call a function in any programming language, what happens? The program counter moves outside the main function usually, and then it does some calculation by means of that additional, that extra program that was outside the main program. And after doing the entire computation with the result, it comes back to the main program and saves the result accordingly and does whatever the main program wants it to do. So you understand what is happening here, right? So this is a very particular case. This is unlike jump instructions. So if you recall jump instructions, in jump instruction, we only jumped around within the main program, right? So in jump instruction, we only jumped around within the main program. And that is why jump instructions were like if, else, and loops, something like that. So through jump instructions, we executed loops. Okay, by jumping back and forth, we created loops. Okay, by jumping to specific points based on a satisfaction of a certain condition, we created if, else like statements, right? So using jump instructions, you can create things like if, else. You can create things like loops by jumping back and forth. But you can never go outside the main program and come back. Using a jump instruction, you cannot go outside the main program and then come back. You cannot do that. Okay? You get the point? So in a jump program, in a program where you have multiple jumps instructions can only make you jump or make the program counter jump within the main program itself, right? Within the main program itself. So that's the difference between a jump and a call instruction. So today we are going to look into call instruction and see how a call instruction actually does this kind of operation. So moments ago, in the beginning of the class, we again recalled a very simple program where we actually added two numbers, right? We recalled a very simple program where we added two numbers. Now we shall do that in this particular scenario by calling a function, just like this one. Okay? And this function, I mean this name function did not come, wasn't there. I mean the function wasn't there, the name function wasn't there in the context of programming languages back then. So you only had something called subroutines. Okay, again the name subroutine is quite popular, quite familiar, rather quite common with Fortran programs. That's why we don't call a function, we call it a subroutine. Okay, we don't call it a function, we call it a subroutine. So yes, let's go back to this and say I'm writing this very simple program. For example, at memory location 8050 I have MBI A comma 25. So register A would get a value of 25. At memory location 8052 I have MVI B comma 35. So register B would get a value of 35. Everything is in hexadecimal, nothing is in decimal. Okay. And in memory location 8054 I had an add B, right? I had this addition. So this is like doing the addition here, right? This is like doing something like this here. This is like writing x plus y here inside the main C program, for example, right? But I'm not going to do that. For example, I'm not going to do that. Instead, what I'm going to do, I'm going to call a function. Call a particular function, or rather call a subroutine that does the addition for me. So I'm going to separate the module that does the addition from the main program here. Okay, that's kind of the context here. Okay, so try to understand that instead of doing the addition here, what I'm going to do at this very point, instead of doing the addition, I'm going to do a call instruction. I'm going to call the subroutine that does the addition. So I'm going to do a call instruction here. So I'm writing call and then name of the subroutine, rather the label of the subroutine. Okay, I'm going to do call and the label of the subroutine. So say addition. Okay, so now I'm going to call addition, and then of course now this call instruction is very much like jump instruction. You shall soon see why. Okay, very much like a jump instruction with certain exceptions, of course, certain advantages. That jump instructions only let you jump around within a main program, but call instruction will let you go outside the main program, and that's the purpose of a jump instruction, a call instruction, to be very specific. It's a 3-byte instruction as usual, so the next instruction would appear 3 memory locations after this one. Okay, so previously this addition was just a 1-byte instruction, something like that. So now I'm doing a 3-byte instruction here so that I can actually call an addition function or rather addition subroutine from outside, right? We cannot write everything in the main program. This is the point here. Okay, the point is not about doing an addition from outside the main program. The point is that we cannot always keep everything inside the same program. That makes the thing very difficult to handle, right? We always write things in functions, right? So of course add 3 memory locations, so I would have a memory location 8057, and there I shall have the halt instruction. Okay, so now of course we called the addition function, right? Addition subroutine rather. So now of course what is this? This is just a label, right? As usual, this is just a label. And what is a label? A label is nothing but an address, right? So you studied that. A label is nothing but an address. So this is just an address, for example. This is just an address. So now say this addition label or basically the address is something like, say, for example, I don't know, say 9050. And here you have the program for the addition. Okay, here you have the program for addition. So for example, let's write down the program. So what am I doing? I'm just doing add b, something very simple as that. Okay, now unlike jump instructions, what happens in a jump instruction? What happens if the condition is satisfied? For example, the program counter is moved to a certain value, otherwise the next instruction is executed, right? Otherwise the next instruction is executed. But the problem with call instruction is that if I call something, I have already gone out of the main program. Right? So I need to have some mechanism to come back to the main program, and I'm going to tell you the mechanism through which it comes back. But instruction for coming back from a subroutine is the return instruction. Okay, is the return instruction, and just as usual, you always return something from, usually return something from a function, something like that. For example, in this memory location 9051, I would have just a return instruction. This is what happens. Let me tell you. Okay, this is what happens. Okay, before anything, just one more thing. Before the call instruction actually makes inherent use of the stack. So let's initialize the stack pointer just before that. So let's start our program from, say, okay, fine, say 8040 4E. For DD, right? Let's say LXI SP, say 5555. So the call instruction makes inherent use of the stack, and I'm going to show you how. Okay, so this addition is just a label. Again, this is just a label, right? Okay, all right. So let's put the stack here. Again, the stack is nothing but a bunch of memory, right? All right. So this is where the stack pointer is pointing currently. So this is memory location. Let me write down. This is memory location 5555. So 5554, 5553, 5552. I don't need much. All right. All right. So this is the bottom of the bucket, rather top of the stack, which is the stack pointer is pointing currently. All right. All right. So this is kind of the end of the bucket, for example, at this very moment here, right? So after executing this program, so this happens, for example. So at this point, what is the value of the program counter? The program counter starts with this address, this particular address. So the program counter starts with this particular address, 804D. So it executes this instruction. Okay. After executing this instruction, the program counter gets incremented by a, so LXI is a 3-byte instruction. Okay, so the program counter gets incremented by a value of 3, so it does execute this instruction. Then the program counter gets incremented by a value of 2, it does execute this instruction. Then the program counter once again gets incremented by a value of 2 once again, right? So it now executes this call instruction, right? So now with this call instruction, the program counter will now be set to this value. Try to understand. The program counter will now be set to this value. 90550, right? The program counter will now be set to this value. Try to understand very carefully here. Now, in order to go back to the main program, the program counter will need to get back to this address, right? Try to understand. The program counter will need to get back to the next address after the call instruction, so that it can actually go back. Okay. So when you do execute a call instruction, what happens? When you do execute a call instruction, what happens is that the memory location, or rather the address of the next instruction. So what is the address of the next instruction? What is the address of the next instruction in the main program after the call instruction? What is the address of the next instruction? The address of the next instruction is 8057, right? And the moment the program counter is set to this address, so after I do the call instruction, what happens? After I do the call instruction, what happens? The program counter is now set to 9050 by means of the call instruction. So this is the responsibility of the call instruction, to set the program counter to the memory address of this particular label. So this is the subroutine, and the subroutine starts at memory location 9050, which is outside the main program, and the call instruction is setting that particular address to the memory, to the program counter. But what happened is, the program counter has completely forgotten what it actually was supposed to do otherwise. If this was some other 3-byte instruction, what would have happened to the program counter? The program counter would have been set to 8057. But since this was a call instruction, it went beyond the main program. So the computer needs to have a way in which it can remember where to come back. Okay, it needs to put a marker on the next address, for example. So yes, after doing the subroutine, try to understand, after doing this entire subroutine, it will have to come back to this. After doing the entire subroutine, it will have to come back to this, right? It will have to come back to this halt instruction to end the main program, for example. But how would it come back if it cannot remember the address, right? How would it come back if it cannot remember the address where to come back? Again, this is not a problem with the jump instruction, because jump instruction only take place within the main program itself, within a particular program itself. So the memory location does not go beyond the main program, right? For example, or beyond the sub particular set of program, right? Now here I have gone beyond the main program. So what happens is, when I do the call instruction, the program counter is set to the memory location of the, so here the program counter is set to the memory location of the particular subroutine. So the subroutine is happening at memory location 9050. So the program counter has been set to 9050. But with that, the program counter has been set to 9050, but with that, it also does something else. Okay, the volume is too loud. Volume was too loud. So it does something else. In order not to forget this, what does it do? It, alongside of setting the program counter with this value, what it does, it takes this address, which is supposed to be the address to which the program counter needs to come back to. This address is actually stored into the stack. So call does two things. It first sets the program counter to the desired address of the subroutine. So here the subroutine was at memory location 9050. So program counter sets the program counter. So the call instruction sets the program counter to point to that particular memory address. and also it takes a return address. What is the return address? The next address after the call instruction, where the program needs to come back. Okay, this address is stored by the call instruction. So this is the responsibility of the call instruction, is stored by the call instruction into the stack. So that is why stack is inherently important whenever you are calling a function. Whenever you are calling a function, what happens? The stack is inherently used by any programming language, for example. So here, what happens is, this particular address, which was 8057, now is stored into the stack. Why? So that I don't forget, so that the microprocessor does not forget where to come back to, right? So it is like leaving your house, and while leaving your house, you just write down the address of your house, right? So that you can actually come back to your house, something like that. It's pretty much like that. Okay, so it's like, so this address where it needs to come back to will now be stored in the stack. So 80 will be stored here and 57 will be stored here. And subsequently, the stack pointer will be decremented by a value of 2. Okay, the stack pointer will be decremented by a value of 2. So the stack pointer is now pointing to this memory location. So stack pointer is pointing to this. So now this is the head of the stack. So in the stack, what do I have right now? In the stack, I have the return address, which is 8057. Again, little Indian byte ordering. So lower order byte comes first and higher order byte comes last. So, right? Understandable? So when I do the call instruction, when I execute the call instruction, what happens? The program counter gets set to the value of the 9050. So value of the label for the particular addition. For example, for this particular subroutine here, I'm doing a very simple addition here. But for any subroutine, what will the call instruction do? The call instruction will set the program counter to the address carried by the label of the subroutine. So after doing the call instruction, what happens? What is the next instruction that is executed? The next instruction that is executed is this one. So addition takes place, right? So content of register B will be added with the content of register A, and then comes the return instruction. Any subroutine should end with a return instruction. Otherwise, it's not a subroutine. Okay. So once I do the return instruction, what does it do? The return instruction, what does it do? It pops the head of the stack into the program counter. So a return instruction, what does it do? It pops the head of the stack. Now, what is there in the head of the stack? In the head of the stack, you have 8057, right? So when I do a return instruction, what happens? It pops the head of the stack, and what is there in the head of the stack is 8057 into the program counter. So after doing the return instruction, what happens? The program counter gets the address back, right? After doing the return instruction, what happens? The program counter gets the address back. So after doing the return instruction, the program counter once again gets the value of 8057 so that it can go back to this particular memory location. So it now comes back to the main program. That is possible because the return instruction actually pops the head of the stack into the program counter. But what was there in the head of the stack? In the head of the stack, we had the return address. What was the return address? The return address was the next instruction after the call instruction. So that was stored as the head of the stack by the call instruction. And the return instruction inside the subroutine, it actually pulls that, pops the head of the stack and pops that head of the stack into the program counter so that the program counter gets back to that particular memory location. So after doing the return instruction here, so this is going to be 9051. After doing the return instruction, what happens? Automatically a pop happens, okay, and the program counter is set to so that the main program can resume. It is not necessary that we are going to end the main program right there. We could have many other programs, okay, but this is how a call instruction and a subroutine actually works. Okay, again, feel free to ask any question that you might have at this point. We have talked about quite a few things. All right, if you don't have any question, so this was call, right? So let's recall our jump instructions. So we had quite a few jump instructions, namely the unconditional jump. Okay, we had unconditional jump. We have jump if there is a carry, jump no carry, jump if the zero flag is set, jump if not zero flag is not set, jump if parity even, jump if parity odd, yeah, jump if the result is positive, so the sign flag is not set, jump if the sign flag has been set, so the result is negative for signed integer operation. Similarly, you have the unconditional call instruction, very similar to those. You have the unconditional call instruction. You have call if there is a carry. You have call if there is no carry. Call if the zero flag has been set. Call if the I was supposed to say jump if not the zero flag has been set, right? So call if the zero flag has not been set. Call if parity even. Call if parity odd. Call if the result is positive. Call if the result is negative. So you have just a complete set of jump instruction and call instructions, and they happen to be they happen to do the same thing, right? Very similar. Okay, jump instruction, what did it do? It jumped the program counter within the same program, okay, based on a satisfaction of a certain condition, right? So jump 0, for example, if the zero flag is set, then the program counter will be jumped to that particular label's address. Otherwise, the next instruction will be executed. The same thing for CZ instruction, the program counter will be set to the label of the subroutine's address. Okay, the address of the subroutine, Okay, if the zero flag has been set. Otherwise, the next instruction will be executed. The same thing. Only thing is that doing the call instruction automatically saves the return address into the stack. So, in a sense, jump and call, they are very similar. They are very similar in nature. Only difference is that a call instruction will, so a jump instruction sets the program counter. A call instruction also sets the program counter. Okay, try to understand this. If I say JMP, something like this, try to see the difference here. Again, once again, I'm just pointing out the difference. If I say JMP label, what does it do? It unconditionally sets the program counter to the address of the label, okay. So what was the label's address? The jump instruction actually sets the program counter to the address of the label. That is what it does, nothing else. So what does the call instruction do? So if I say call label, what would it do? It will do the same thing. It will set the program counter to the address of the label, right? It will set the program counter to the address of the label, but it will do one more thing. In addition to that, it will push the return address to the stack. Okay, so if I say jump label, the program counter is set to the label's address. If I say call label, then also the program counter is set to the label's address. Only difference is that a call instruction, in addition to setting the program counter to the label's address, it will also push the return address to the stack. So when you do a return instruction inside the subroutine, you can actually come back. So that is why call and jump are very similar with a subtle difference. And this subtle difference allows call instruction to call subroutines, go beyond the main program and do subroutine. Okay, and you can also do nested subroutine calls, like just like nested function calls. You can do all these things. Okay, all right. So this will be the end of today's class, and if you have any query regarding any of the things that we discussed today, and on the next class we shall be doing quite a few program regarding based on these, and then on the next class we shall jump into interrupts, because interrupts are inherently associated with call instructions. They are very similar to call instructions. We shall see. Okay. All right. So if you have any query, feel free to ask at this point. All right. So if you don't have any more queries, we shall end our discussion today at this point. So in the next class we shall be talking about we shall be doing a bit of programming with the jumping call instructions. We shall see how subroutine actually really works out with different conditions. All right. So thanks for being here. I shall see you on maybe on Monday. All right. Thank you very much.